This last section of MAC 1105 is dealing with exponential modeling. So what we're going to do is look at a model that can be either a growth, an exponential growth, or a decay model. It depends on whether this exponent right here, k times t, is positive or negative. So if you find, and since time is always going to be a positive function, the k is the rate of growth or the rate of decay, and that's the part that's either going to be positive or negative. So we can write it as a function of time, which is t, is equal to the beginning amount times e to the power of that growth or decay rate times the time allotted. And the way we usually look at it is this way. We look at it as the final amount, which would be the final function, would equal the final amount that it's going to equal. It's either going to be the beginning amount plus something or minus something to give us this final amount, depending on whether it's a growth or decay model. So what you really have to memorize is this particular format, and you might want to remember it that it is a function so that you can write it as a function later if you need to. Let's take a look at the first problem, which is on the next page. And there aren't many of these because you can see they'll all sort of follow the same pattern. So this one says in 2000, the population of the country was approximately 6.37 million. And by 2060, it's projected to grow to 11 million. So we want an exponential growth model, and we're going to use that same format. And T is the number of years after the year 2000. So 2000 is sort of our base year. And we want to first, part A is find the exponential growth function. So what they're really saying here is find K, because that's going to give you your function. All you have to do, the only thing we really don't know is what K is. So I'm going to go down to a blank sheet of paper because I think I can show this better here. And for 1A, I'm going to write down everything that I do know from this problem. First of all, I know that its beginning population of this country was 6.37 million. So in my format of my function, that's going to be a to the 0. That's going to be a base 0, okay? So that's going to be my base amount, and it's going to be 6.37. Everything's in millions, so I don't need to write all those zeros. And then the next thing they tell me, it's projected to grow to 11 million. So that's going to be the final amount that it gets to. I'll write that as A. So A is going to equal 11 million. Now, it'll really help you if you have this function written down. So what the formula is, A is equal to A base 0 times e to the power of kt. And of course, what we said we need to find is k. We need that growth. We need the growth for the growth rate so that we can get the growth function there. Now, what do I know about time? Because that's the other unknown. I know what e is. I know what a base 0 is. I know what a is, but I don't know what time is. And they said here it's going to be the number of years after 2000. And they did give me an amount here that I'm working with. I'm working on the growth up to 11 million, and it was from that was in 2060. So I'll say time is equal to that difference in 2060 and the base year, which was 2000. So of course, time for this one is going to be 60. Now, if I just have the one unknown, even if it's an exponential unknown up here, I can find what my growth function is. So I'm going to start solving it. I'm going to set it up and say 11, which was A, which was the final amount, it's going to be 11 million, is equal to that base population of 3.7 million times E to the, and I don't know what K is, but I do know time now. I said this happened, 11 million happened after 60 years. So the only thing unknown is in an exponent. It's the exponent that has the k as part of it. So that means I'm going to have to use some type of log to solve it. Now, picking the log for these is easy because we have e to the power of this. And so we're going to use the natural log, or ln, every time. And before I can do that, though, I have to be taking the natural log of something with a coefficient of 1. And this has a coefficient of 6.37. So I'm going to divide both sides of this thing by 6.37. And when I do that, I end up with a decimal. And I'm going to take these decimals, most of them, to 4 decimal places. But then if the calculator has more and it's I can do it as a continuing, the answer divided by or whatever, I'm going to let it use that extra precision. So what I came up with was 1.7268, and it goes on. I'll just write down 1.7268, and then that's equal to e to the power of, and let's reverse those and say 60k, because that's the way we're used to looking at our variables is listed last. Now, I'm going to solve this by taking the natural log of both sides. I picked the natural log because I have e raised to a power. So this is really the natural log of 1.7268, and that would equal the natural log of e raised to the 60k. Now remember, because we did this in the last section, you should be able to remember this. This is the natural log. It's log e. It's log base e of e, isn't it? And so what this is all equal to, when we have the natural log of e to the power of something, we can get rid of the log and say it's just equal to whatever the exponent was. Only happens when you have the same log as you have what it's taking the log of, okay? So now I have 60k over here, and over here I'm going to say, well, that's equal still. I didn't get to do the same thing on the other side, so it's the natural log of 1.7268. Now that was what was in my calculator. It's that number, but let's find the natural log of that number. So I say ln 1.7268, and then what am I going to do to it? Well, what I'm really going to do is divide it by 60, right? So rather than get all of these intermediate results, let's just go straight to what we need. This would give me k, and all I have to do is say the natural log of 1.7268 divided by 60. And what I came up with is a really long decimal. Now, I need always for these decimals, they're going to say you need 4 significant digits. Now, the digit after the decimal is a 0. That's not significant. This 0 is not significant. It starts here. The 9 is significant. I need 4 including that. So I need 9, 1, 0, and 4. I wouldn't round it up since the next one's a 4. So I'm going to say this is equal to 0.009104. You can end up with these decay and growth functions. You can end up with quite a long decimal, but remember, after that decimal point, you have to hit something that's not a 0, and then you count 4 digits after that, okay? And be sure you round that 4th one. All right, so I've got my rate now is k, and it said what is the function that models it? Well, I would say, if I was writing it as a function, I would say it's a function of time. So I'll say f of t is equal to, and I'll use this, it would be equal to a to the power of 0 times e, or a base 0, sorry, z, e times, and I'm going to say my exponent's 0.009104 t, isn't it? And I've written it back in a function that I can use, and this would be the function I would be able to use to answer questions. And now they've given me a question. The question is, by which year will the population be 10 million? Well, I've got my function. T is the unknown. So I'm going to say, okay, I want to know by which year that will be. Okay, so I'm going to say this is going to be a function of time this time, isn't it? And that's the way my functions will work. So what I have to really think about is, what is that answer going to be? In other words, this is still A, the final amount, isn't it? And they told me by which year would it be 10 million. So what they've redone for me is they've redefined A. They want to know, when would A reach 10? When would this part of it reach 10? Well, it still started at 6.37. So I've still got the base number, A sub 0, or A base 0, is still 6.37, okay? So now I have everything except for this unknown time, and that tells me how many years past 2000, which is the starting year for this thing, how many years past 2000 it's going to reach that 10 million number, right? So let's go ahead and plug it all in. I'm going to say 10 this time is A, and that's equal to the base number, 6.37, times e to the power of, and there's my growth function, 0.009104, and I don't know t, and there's t. So I have one unknown, and my unknown is in the exponent, so the only way to solve it is to take a log. Now this time, I'm going to divide both sides by my 6.37 because remember, I can't take the log until I have a coefficient of 1 out here. And I'm dividing 10 this time, divided by 6.37. And what I come up with is 1.5699, because I'm going to go to 4 decimal places here. So I've got 1.5699, and that's equal to e to the power of 0.009104 times time, the number of years. Only way to solve this is to take the log of both sides. And I'm going to use the natural log since my exponent is being raised from the power of e, right? From the base e. Okay, so I'll say natural log of 1.5699 is equal to the natural log of e to the 0.009104t. Now, this once again is the log base e of e, isn't it? That's going to just be equal to that exponent. So I did get rid of my log over here. And now my unknown is not in an exponent anymore. But over here I have to take the natural log of that number. So I'll say natural log of 1.5699. And I'm going to end up dividing it by this, right? And you can do that all in one step if you want to. I'll go ahead and write it down for you. What's happening here is I'm going to go ahead and say divide both sides by this number. Okay, so it's written out for you so you see what I'm doing. All right, all I have to do now is I've got the natural log of 1.5699 divided by 0.009104. And that should be right. All right, let's divide it. Of course, this one cancels out, doesn't it, on this side? So all I have over here is t. That's going to be the number of years. And what is that number of years going to be equal to? Well, it helps when you put division and not what I put. Hang on just a second. I'm going to go ahead, since I've got all these numbers in, and enter it down here again. And then I'm going to go and change this one to division. Okay. Okay. 0.009104. I think I got that right this time. Let's see what it does. Oh, much better answer. So I came up with 49.539 years. So let's just call that 50 years, okay? We'll round it since we've got 49.5. We'll say t is approximately equal to 50 years then. And then what we're going to say is, did they ask us which year? Which year? Okay, so what are we starting at? Well, the base year was the year 2000, wasn't it? So 2000 plus our 50 years is going to equal 2050. So at 2050, we should have a population of, what was it asking us for? 10 million. So let's do another one. This time it's the population of Vero Beach, which was 15,145 in 2010. And in 2020, it was 16,962. Now, if we've got the two dates and the two populations, we can calculate that growth function. We know it's a growth. We know it's increasing. We know it's going to be a positive exponent then. And we know the time, and we know the difference in the two populations, so we should be able to calculate our growth function. And that's the first thing they ask us to do. So for 1A, we're going to take this information and calculate the growth function. I'm going to write down what they told me. They told me that in the base year, the amount or the population for that base year was 15,145. And they told me in the ending year, which is the amount that it equaled when it finished growing, it was 16,962. And the time it took for that to happen was the difference in 2020 and 2010. So I would take that bigger number and subtract that smaller number, and I'd say, well, it took 10 years for this to happen. So that's my 10 years growth. Now, if I know those three things, there's only one more thing in my growth function calculation, And so I'm going to write this down and fill in the pieces. This is my formula that I'm just memorizing. So I'm writing it every time so that I make sure I have it. And I'm going to just fill in the pieces here. I've got 16,962, and that's equal to that base population of 15,145 times the number E raised to the power of some unknown times the time of 10. All right, now my exponent is my unknown is in my exponent. So I know I'm going to have to take the log of both sides, but I can't do that until I have a coefficient of 1 here. So I have to divide both sides by 15,145. So let's see what I get when I do that. I'll do 16,962 divided by 15,145. And of course, over on this side, I'm going to have e to the power of 10k. And over here on this side, I'm going to get 1 point, and I'm going to go to 4 decimal places, which is going to be a little problematic for me because that fourth one is a 9, and the fifth one is a 7, which means I have to go up. That will turn that 9 into a 10. I'll have to go up again. That'll turn that 9 into a 10. So really, I'm going to go to 1.12 is what I'm going to go to. So I'm going to just keep on with my decimals here, 1199, and add another decimal just because I'm not sure. You'll have you'll have a clear indication of how many decimals to round it to, but I kind of like to have more than, or at least 4. So I'll keep the fifth one since it was going to take me to 2 significant decimal places. And then I'm just going to do the log, or the natural log of both sides. And the reason I'm doing the natural log again is because I've got e raised to an exponent, and I want to get rid of that. I want to get rid of this log, and I can if I have the natural log of e. So I will now have, this is equal to the exponent 10k, and this is the natural log, of course, of 1.11997. And now all I have to do is divide both sides of that by 10, and I'll have what k is equal to. So easy to do. I'm going to go ahead and put it all in one step in my calculator here. If I can get it so we can see it. So I'll say the natural log of 1.11997 is going to be divided by 10. And I get k, the rate, which is going to be a growth rate. It's positive, 0.01133. I do need 4 significant digits that are after the decimal. The 0 doesn't count, so I'm going to go to all 4 of these. And the next one, I didn't have to round up because the next digit was a 0 here. So I've got k. I can go up here and say, well, the k is equal to 0.01133. I know that. And so whatever question they asked me, that first question was determine the function, the growth function. Now, if I wanted to write this as a function, I would say then function of time, wouldn't I, is equal to a to the power of to the base of 0 times e to the 0.01133t. So I have it written as a function. Now, what's the next question? The next question was predict the population of Vero Beach in 2025. So that's going to be my ending year now. So 2025, how many years past the base year is that? Well, the base year we had was 2010, wasn't it? So they've given me time. Time here is now going to equal 2025 minus whatever the base year is, and it was 2010 was the original year that I was given the growth, the beginning growth of Vero Beach. So now they're asking me to say how much it would be 15 years past 2010. All right, I have everything else. Everything else is the same. I have the base population. I don't know A. I don't know the final amount. That's what they've asked me to find. But they've given me time, and I know my growth rate. So I'm going to plug all this into this formula. It would be A is equal to A base 0 times e to the kt. So a is equal to the unknown this time. So that's the part I don't know. I know the base year population. I know what e is, and I know I'm going to raise it to the power of 0.01133. How many years am I going to use? 15. Multiply those two together. Now, this is not take a log of anything because the unknown is not in the exponent. E is not an unknown. We know what E is. It's even a function on our calculator, button on our calculator. What do I not know? Well, I don't know A. I don't know the final population. So this is easy. I just type this in and let my calculator do the work for me. I'm going to say 15,145, and then I'm going to say times E. Now, where do I find E? It's right above this division button, isn't it? It's that right there. So I'm going to say second, and the division button, I've inserted E, and then I'll say to the power of. And I have to multiply these together, so I have to put them in parentheses. 0.01133 times 15. Now, those in parentheses around that exponent is very important. Otherwise, it'll do e to the power of 0.01133 and might not multiply it times 15, depending on your calculator. It might multiply the result times 15. So don't take any chances. Just put it in parentheses. Let's see what we get. So I get for this one, the ending population is going to be 17,950.5. I'm going to round that. I'm going to say the amount's going to be really close to 17,951. I'll use whole numbers since it's people. And that's the population. What did they ask me? That's the population of Vero Beach in 2025. All right, what's the next question? Predict when the population will reach 26,883. Now that's a new ending number that they've given me. They've now told me that the ending number is going to be 26, what was it, 883, right? Okay, so this is a new problem. What else do I not know? Well, I don't know the time, obviously. Time is what they want me to solve for, but I think I have everything else. I know the beginning number. The beginning amount is what it always has been set to be. It's 15,145. I know K. I know the growth rate because I calculated that. The only thing I don't know is time. Time this time is my unknown. They said, what year is it going to reach that? So I'm going to take my formula and write it down again because I'm working at memorizing my formula. And I'm going to say the amount that I want to end in, I want to end with 26,883. And I'm going to begin with 15,145 times E raised to the power of 0.01133 times time. So there's my unknown in the exponent again. Since it is, I know I'm going to take the log of both sides, but first I've got to get this coefficient to be 1. I'll divide by 15,145. And then I'll have E to the power of 0.01133t. And let's see what that's equal to on the other side. So I'll say 26,883 divided by 15,145. And I get 1.7750. I can use that. 1.7750. Didn't round up because the next digit was a 4. And now I need to take the natural log of both sides. All right. Doing this side becomes equal to the exponent. And over here, what I've got is the natural log of 1.775. You don't have to write the 0. And what I'm going to do in the end of this is divide both sides by 0.01133. So let me see if I can't do that all in one step. This will turn out to be just t, 1t. And I'm going to take the natural log of 1.775 0.0750. And I'm going to divide it by 0.01133. I think I got that right. And I end up with 50.6. Now this is in years. This is time that I've got. So I'm going to round it up to the next whole number for years. And I'll get 51 years is about when it's going to get to that population. Well, 51 years after what? After year 0, the year where this amount was true, where it was 15,145. It started in year 2010. So now I have to say, well, 2010 plus 51 to get me whatever year that's going to be. And I end up with the year 2061. Now for our last problem, we've been working on population increases. Population can decrease too, so you could have had a decreasing function there, but we didn't. But now we're going to look at a decreasing function with an interesting case. This is about Marie Curie. She was a pioneer in physics and chemistry. She pioneered the radioactivity research. She discovered certain elements, and she died from complications linked to high exposures of radioactive elements, specifically polonium, which she had discovered and named after her native country of Poland, and radium. She was exposed for many, many years to these elements, and so to this day, her remains are dangerously radioactive. So she has been entombed in a lead-lined coffin. One of the isotopes, radioactive isotopes that she studied is radium-226, and that particular one has a half-life of, let's say, 1,600 years. I think the actual number for that is something like 1577, but we're going to say it has a half-life of 1,600 years. Now, how many years would it take for the amount of radium-226 on the remains of Madame Curie to go down, to reduce to 6% of the original amount that was present in her body when she died in 1934? So that's the interesting question we've got in front of us, and it is going to be a decreasing function. We know, because we know these levels of radioactivity are going down at an exponential rate. So let's see if we can figure out what it is. Now, what have they told us? Because that's going to be key in figuring out what we need to know. They told us that they want to know when it's going to reach 6%. Okay, when it would reach 6% would be 0.06. And that's going to be the amount we want to get to, isn't it? The final amount we want to get to, because we got to come up with this decay rate before we can do anything. So then we're going to say, okay, what was it in the beginning? What was it at the base year? Well, it was 100%. When she died, it was at 100% exposure, and that's really equal to the number 1. So we've got some pretty good numbers to work with. We just have to think, okay, it's going to go down. We want to know when it gets down to 6%, which is 0.06, and we start from there at 100%. And we're not saying you're not saying, you don't know what her exposure is, but her total exposure was 100% of her total exposure. So that's always going to be 1. Now, the next thing they told us was that this radium-226 has a half-life of 1,600 years. Now that means that every 1,600 years, it will be half as strong as it was in the beginning. So it only takes 1,600 years for it to go to half, and then we take another 1,600 years for it to go to half of that. And so what will it be? How long is it going to take it to get to 6% of the original 100% is the question. So what is the time? We're going to have to figure out the rate. Well, we're going to use the time here of what we know. We'll start with the first time, 1,600 years. And then we'll say it started, it's a half-life, so it's going to decay how much? Well, it's going to decay by half, by 0.5. In 1,600 years, it will be half of what it was. It will be 0.5 of what it was. And the ground zero, of course, it was 1%. It was 100% or 1. So this is what we have to do to find what k is equal to. We have to say it had a half-life of 1,600 years. That means in a time of 1,600 years, it will go to half of what the original amount 1 was. This is the question we're going to have to answer, but we have to do this to get there. All right, so what is our formula going to tell us? Well, we know we can say A is equal to A base 0 times e to the kt, right? And what I don't know is this, t. Everything else I can fill in. I can say it's going to get to half of its strength at, and it'll be 1 times e to the k, and it's going to only take it 1,600 years to get to half strength. Now, I can solve for this unknown k because I had the pieces. And this is a coefficient of 1, so I don't have to divide both sides by anything before I take the log. I'm going to say ln, the natural log of 0.5, is going to be the natural log of 1, well, I don't have to write a 1, of e to the power of 1,600k. Now, I have to figure out what that is, but the natural log of e, I can say that's equal to that exponent, 1,600k. And then what is it? Well, it's the natural log of 0.5. And then once I finish this, I'll be dividing both sides by 1,600, won't I? So I can do all of that together and find out what k is equal to. So I'm going to say natural log of 0.5 divided by 1,600. And I came up with a negative number. Now, that's right. We know that's right because we know that this is a decreasing function, because we know in 1,600 years it'll only have half the strength it had, so this is going to go down. So we know we have to have a negative exponent. I've got negative 4.3321, but wait a second. This says e to the power of negative 4, which means take the decimal and move it 4 places in a negative direction. So I'm going to be pushing it back. So what am I finding k is equal to? Well, it's equal to a negative number, and then I'm going to take that decimal, and it'll have 3 zeros in front of it because I moved it just past the 4, and then I moved it 3 more places. I had to insert 3 zeros. So there's my 4. I moved it 4 places to get there. And now I need 4 significant digits. Well, I got the 4, and I need 3, 3, and 2. The next digit was a 1, so it doesn't change my 2. So I ended up with negative 0.00043332, and that is my decay rate. It's a very small decay rate, isn't it? All right, so now, what is the next question, or what is the question I've asked? Because it says how many years are required for it to get to 6%. Okay, well, I found out, how long really, this is how long it's going to take to get to half the strength is 1,600 years, and I use that to find my decay rate. So now let's see if we can plug it in and say, what's it going to take to get to 6%? 6% we know is going to be 0.06. That's the amount we're interested in getting to. It started at 1, didn't it? And then I can say times e to the power of negative 0.0004322, and it's times time, t. There's the unknown. Now my exponent is where my variable is, so I have to use logs. This is a 1, however, so I don't have to divide both sides. I just have to take the natural log of 0.06, and that's equal to the natural log of e to the negative 0.0004322t. And what I'll do is say this is really equal to the exponent, negative 0.0004322t. What is the natural log of 0.06? So let's divide both sides by this negative number, negative 0.0004322. And this natural log of 0.06 will be divided by negative 0.0004322. Let's see what happens when we do this. I'm going to say the natural log 0.06 divided by negative 0.0004322. Let's see what I come up with. There's my years. It will take 6,509 years, 0.5. So I'm going to say 6509.5 will equal time. I'm going to round it up and go to 6510. I'll say 6510 is the number of years it'll take. Now, what year did we start this thing? If you want to know, I mean, that's how many years it'll take. And that was the question. How many years are required? And it'll take 6,510, approximately that many. If they say go to whole numbers, that's what I would do. But what year is that? Well, she died in 1934, didn't she? In 1934, plus that 6,510, we're going to go to, what year is it? 1934 plus 6,000, plus, let me do it again, 1934 plus 6510. The year will be 8444. So that would be the year that she would only be, her remains would only be at 6% of what they were when she died.